Hey, okay. Third week and our third remote lab, and probably the one that I think I'm going to struggle the most with trying to make it come across on the screen because we've got some drawings to do. And so I'm going to send some of these drawings in a PDF form to you. And so you can watch us work with them, but you've got to kind of make your own little drawing and then expand on that drawing. And so I will do the raw data and have the raw drawings. Here's our drawing board. And then I will scan them. And so as I'm sending out this video lab to you, I will also send out these in PDF, and then you can decide as you do your drawing on top of it if you want to print it and then just do kind of an old school draw on top of it and scan it and turn it in, or I know some of you have some really nice where you can write on the screen, and that's fine too, and the drawings don't have to be real accurate. In fact, I'm going to go a little faster than we normally would when I do my drawings here, because it would be kind of boring, I think, for you to sit there and watch me do the drawings. And so so our drawings won't be perfect, but I think the lesson will still be there. In fact, speaking of the lesson, let me begin by not showing you the equipment yet, but coming over here to the whiteboard and start working on the theory behind it. In fact, I'll even say that if you have not already looked at the video lectures for this chapter 25, or I guess it's 7 in the OpenStax book, 25 in the Survey book, go ahead and watch that lecture first and read the chapter, because there's something very important in there that I want to point out now here. So come over here, and in this chapter 25, the author introduces you to potential energy. And maybe introduce you is the wrong word, because you were introduced to potential energy actually in the chapter on conservation of energy back in Physics 121, and this was that definition. And if you've gone ahead and watched the lecture here, you'll know that in the lecture I talk about this. I said, okay, you guys did this back in 121. Of course, what you did in 121 is you implied that the force was the force of gravity. So we talked about the gravitational potential energy. Well, today, of course, and in this course, we're talking about a different force. We're talking about the electric force. So to make that kind of clear, I'm going to put a little sub E under here and say, if you integrate over space, over distance, a line integral of the electric force with a negative, you get then the electric potential energy. Now, another thing you'll see in the lecture and the reading is don't confuse electric potential energy with electric potential. So let me take one more step here. Let me replace the force, the electric force, with the electric field times its charge. And then let me move this over to the other side. And over here on the right-hand side, I have an integration of the electric field over some line, some distance. And this right here, the energy per charge, per charge, is what we call the potential, the electric potential. And so this lab today is, of course, kind of helping you understand the chapter for this week. And that is trying to understand what is electric potential energy, what is electric potential, and how is it connected to the electric field that we have been doing for the last 2 chapters. And this is it. This is what I'll call the working equation, if you will, for this lab. for this lab, we are going to see, and let me just use my words I love to say, is let's read the math a little bit here, and let's see what this equation is saying. Starting with this idea of electric potential. So electric potential really is how much energy would you get if you put one charge there. The units, as hopefully you caught in the lecture, are in units of volts. So we will start labeling things in terms of volts. A good example is like your car battery is 12 volts. And what that really means here is if 1 coulomb of charge would move from the negative terminal to the positive terminal, then that would be 12 joules of energy. Because the 12 volts means you get 12 joules of energy for every charge. So we're going to work with potential here today, electric potential. We're going to measure things in volts. And so I'm going to go over here in a little bit and set my little apparatus at 10 volts. And we're going to look for places that are 10 volts, 9 volts, 8 volts, 7 volts. And so if we find something that says 7 volts, we hopefully know what that means. But that's not so much the main purpose of this lab. The main purpose of this lab is to draw a nice conclusion out of here that if you study this equation carefully, there's a nice geometric pattern between the electric field and the potential. And maybe you can see it if I were just to put a positive charge. Let me put just a little point charge, the simplest one I can think of, and draw the electric field. Now, I know in the survey book, the author color codes the electric field in kind of a burnt orange, and this is about the closest I have to a burnt orange. It's more of a brighter orange. But I'm going to go ahead and draw what might be the visual effect of the electric field from a point charge. And so here's that equation. Electric field is Coulomb's constant times Q over R squared. Although now we're a little more advanced, we can replace Coulomb's constant with what Gauss did, and that is to say Coulomb's constant is really made out of two other factors. One is the geometry, the 4 pi, and the other is how the electric field is affected by the material around it. We're pretending there is no other material around it, so we call it the permittivity of free space. All right, and so this is now our working equation for the electric field from a point. Okay. Now, if you look at this electric field, here's what it's saying. It says, if you go in the direction of the field, in other words, if you move along a distance that's in the direction of the field, right here, so this is in the same direction, and this is a dot product, so this would be cosine of 0, that would be a positive number, and with the negative would make this a negative, would make it a decrease. In fact, maybe I should write it from some initial point to some final point, then this would be that change in potential. So if I came over here and put, like, say right here and say, okay, this is the initial point and I'm going to move right here and this is the final point, then if I were to move from initial to final, I would be going with the field, right? And so let's study this math. Moving with the field, this would be positive, multiplied by a negative means I would have a change in potential, which is negative. So as I move away from a positive, I would be going to places of lower potential. When I go with the field, I am going to places that have lower energy. This is really no different than we did in 121, right? If we took some object like this marker and I held it up here and I moved it from here down to here, I moved in the direction of the field, the gravitational field. This down here is at a lower potential than this up here. Exactly. And so what we did with gravitational is still the same thing we're doing here, it's just now electrical. And maybe it'll be a little less familiar with you. And of course what we didn't have is we didn't have both a gravitational attraction and a repulsion like we do with the electric field. So there is a little more complication to this electrical stuff compared to gravity. But I just wanted to point that know this, that as you go from a positive to, say, a minus, you're going to decrease in your potential. Or the other way around, if you go from a minus to a positive, so in other words, if you go against the field, you're going to increase in potential. That's what this is saying. Maybe I should point out the math. If I was here going the other way, if I went from final to initial, if I went from here to here, I'd go against the field. And so this dot product would have a cosine of 180 degrees. The direction of the field and the direction I'm moving would be 180 degrees apart. Cosine of 180 degrees is a -1. You put that -1 with this negative, and the change in potential then is positive. That's what this math is saying. Okay? And so maybe up here, I will just put, so this would be high potential, and this would be then low potential. And either way, whether I start here and go here, I go low. If I start here and here, I go high. So I can actually label this as high potential and low potential. Now, there's something else, and this is the main point to really understand why we're doing what we do in this lab, is what if I were to move 90 degrees to the electric field? So again, let's talk about this initial point and say, what if I were to move 90 degrees? And so 90 degrees, I'll just put a little hash mark right there and say, okay, so I'm gonna move perpendicular to that electric field. See, if you come back here in the math, you are moving at 90 degrees to the direction of the field. So the dot product here, you would say you would have a cosine of 90 degrees. Maybe I should even write, this is E, the magnitude of E, times the magnitude of dr, times the cosine of the angle between them. So again, if I were to move 90 degrees, I would have cosine of 90 degrees in here. And cosine of 90 degrees is 0. So as long as I always move at 90 degrees to the electric field, this would always be 0. And so if you add up a bunch of zeros, you still get 0. And if you take the negative of that, you still get 0. And so this is saying that the potential does not change when you move at 90 degrees. So in this very simple picture, if I were to move maybe in this pattern, which would be the pattern of a circle, I would always be moving at 90 degrees, and therefore this is saying that there'd be no change in potential. So if the potential at this point happened to be, say, 5 volts, then everywhere along this black line would also be 5 volts. Now, why don't we do what I labeled the lower one here? Now, as I said earlier, if I were to move from this initial to this final, I would be going with the field. And as I go with the field, that would be a decrease in potential. There's that negative again. So maybe just for reminding myself, I'm going to put a little 5 volts here on that black dotted line to remind myself that that's 5 volts. Okay. So then, that means this would be lower than 5 volts. Now, I didn't put any numbers in here, so I don't know exactly how much lower, but let me just say it goes down to 3 volts. All right. But if I were then to draw a line or to move always perpendicular to the electric field, that would always be at that same volts, 3 volts. So I'll label that black line as 3 volts. And so a fancy word we like to use here is we call these equipotentials. And these equipotentials are perpendicular to the electric field. All right, so this is the foundation of sound picking up okay? Yeah, we got some construction on outside here, so it's getting kind of noisy, but I think it's about to fade away here. All right, but what I want you to understand as we get started here in the lab then is this, that the equipotentials are perpendicular to the electric field. So what that means, and we could go either direction, if we know the electric fields, then we could find the equipotentials because they'd be perpendicular. What we're going to do in the lab is the other way around. We're going to find the equipotentials, and from that get the electric field. So you are asked, and I will hook up and work with you here in just a second, to create 3 different charge distributions. The first one is kind of the classic one that you saw, you saw mostly with Gauss's law in chapter 24, or chapter 6 in the OpenStax. And that is, what if you took a plate that was charged, charged, positive and negative. What would that electric field look like? And so that's going to be our first drawing. Our drawing is going to first, and this is what I'm going to do with you, I'm going to go over here, I'm going to use this equipment, and I'm going to find all the equipotentials. Well, I shouldn't say all of them. I mean, obviously there's a whole grading, but I'm going to find enough that we can kind of get a pattern. So like back here, I did a 5 and a 3 on this one. This I'm going to charge up so it's 10 volts higher than that one. And so I'll do a 1 volt, a 3 volt, a 5 volt, a 7 volt, and a 9 volt. And so we'll have enough equipotentials that then, once we have those equipotentials, we hopefully will be able to then draw the electric field. Now, the second one, and maybe I'll come back to draw this on the board, so I'm going to leave that one alone here for a second. The second one is kind of the famous dipole one. And both of these are very common ones, and ones that the reason we want to do this in the lab is you should really have these 2 memorized in your head. You know, have a picture in your head of what does the equipotentials and the electric field look like for 2 parallel plates, and then what does it look like for 2 points that are equal and opposite charge, a dipole. And then the third one is kind of this fun one that will kind of combine the 2, and I'll maybe start to show you the equipment here. But what would happen if you took then a positive point and a negative plate? What would the field look like from that? And hopefully what you will learn here is, by knowing these, I can kind of combine and get this. And so hopefully as you become more familiar with the fields, I could give you any kind of shape, and you could roughly kind of sketch, kind of guess what the electric field looks like. So I can give you maybe an L shape next to a U shape, and some of these can get pretty complicated. So it takes a little bit of experience with it, and this is our first step, our 2 fundamental beginning ones. And maybe I even shouldn't say fundamental, because this dipole is actually a step up from just the single point one. But I'm going with the idea that you kind of understand the single point one. We've done the electric field from a single point quite a bit. And now this is maybe the first time, or maybe in the lecture, it's certainly the first chapter, that you've seen the equipotentials. But I should say know that one too. That one just seems so obvious, basic maybe, that we don't do that one. All right, so let's come over here to the equipment here. And so let me show you the equipment. I'll start with this. This is called a voltmeter. It measures the volt. Really, a better word is it measures the electric potential. So this is going to measure the electric potential. This little device here, my power supply, is going to actually give me the energy. The power supply is going to tell me what it is. So if I hook up, and so you can just kind of see my little drawing table on the underneath side. I have a parallel plate. In fact, I grabbed an extra one here so that I can kind of show you this is what we're charging up. There's our parallel plate. This is the one we're going to do first. All right? And so what I'm going to do is charge one side negative and one side positive. But I got it mounted onto my drawing board. And you'll see why in just a second. So right here, this one is going to be the negative plate. And it's actually clamped on and goes the, excuse me, the charge, if you will go through this metal piece down here. And when electricity goes through a metal piece, it's called a bus. So there's a bus under here. In fact, let me grab another one. You can kind of see the bus. Here's one without the plate on it, without the parallel plate. But right here is that metal bus. And so I just put the screw into here. Because what's important here is on the top side is this black connector, which is then connected to this power supply here. Okay? So you might want to zoom out. I don't know. Can you see all these three things in one shot? Or oh, okay. But that's the idea, that these are connected here. Okay. Now put that aside. All right. So this right here is connected to what I'll call the 0 volts. Now the same logic is true over here. This is the positive one. Okay. And so if you look, I've got a red wire, which if I trace it over to here, comes back to my power supply. See, and so my power supply is set at 10 volts, saying the voltage between these two wires is 10, and all I've done is hooked up my metal piece, and that should transfer it. In fact, this will give me a chance to come back over here and read the math. Watch, let's look at this equation again. You've hopefully already learned by this time, what is the electric field inside a metal conductor? And the answer is 0. So if you put 0 here, so if you're in a spot that has no electric field, this integral would be 0. What that means then is, in a spot where there's no electric field, so in a metal where there is no electric field, there is no change in potential within that piece of metal. Ah, good. And that's what I'm taking advantage of over here. If I come over here, I have a wire, a piece of metal. This is made out of copper wire. And this machine here is saying this is at 10 volts. So once I hook up this piece of metal, there's no electric field inside of that piece of metal. So that means this spot right here is also at 10 volts. And when I connect it to that metal piece, which is connected to this metal piece, which is connected to this bus, this metal piece, which is connected to this screw, which is this metal piece, which is connected to this plate, which is just painted on aluminum, so it's another metal piece. All of these metal pieces are connected together. There's no electric field, and so there's no change in potential. And so this machine set it at 10 volts. That 10 volts is essentially transferred to here. That's what that says. No electric field means no change in potential. All right, so what I should have then is I should have this metal plate at 10 volts and that one at 0. So to give it a little test, kind of see how the equipment works here, let me take my voltmeter, so I'll kind of point it towards you so maybe you can see. And so I'll also show you the bottom here where I'm touching. But if I actually touch this metal plate, there it is. It says it's 10 volts. And if I touch this metal plate, there it is. It says 0 volts. And that means between these two, there's an electric field and a change. Why don't I just touch it about halfway? I suspect that's going to be about 5 volts. So right here, looks like I'm touching it at 4.82. Closer towards the 10 plate should maybe be around 7 or 8 volts. So there it is, 7.5. Touching it close to here should maybe be between about 2 and 3 volts. So there's 2.6, right? So there is then my electric field. It must be going this way. It, of course, points from the, the electric field will go from the plus to the minus. So I expect to have an electric field kind of this way, and then equally spaced are probably my equipotentials. And that's what I'm going to find here. Like I said, our goal here is to find out what does the electric field look like from this parallel plate? Now, so I can draw it, I'm going to draw this on the top. And it's kind of a neat design. It's a very clever design. This is when I really wish you guys were here to do this. It's just kind of neat to see. So here is what I'll call my probe. I'm going to connect it. And this is a piece of metal with a wire that comes out to this little metal copper ball here. And so what I can do is slide this probe in here. And the probe's actually touching from the bottom side. If I try to get the middle, this kind of looks like the middle, I should probably be touching it, and my meter should read about 5 volts. And so it's reading 4.5. If I move the probe a little bit closer towards the positive plate, it should go up a little bit. Yeah, there's 8.7. And if I move the probe the other way, oops, it's too far, I felt it bump, that should read a low voltage. Yeah, 2.3. Okay? And so I am essentially, if we're looking at this picture here, touching it between these two. And maybe if it'll be okay with you, I'm going to go ahead and in my drawing up here, change all these to positives and all of these to negative, because I just noticed as I hooked it up to you guys would be looking like this, and so to your right would be the positive connection and to your left would be the negative, just so kind of consistent here with our equipment. All right. Now, of course, it's on the bottom, and so you might be asking, how do you do the drawing? Well, again, this is really neat about this design. It's kind of clever. You're not going to actually draw on those metal plates. We're going to draw on this piece of paper. This will ultimately be the piece of paper that I'm going to send to you in a PDF. And the table, the drawing table, if you push down on it, the legs are these spring-loaded rubber stoppers that are a little worn out with age. I can spray some WD-40 on them, but they should tighten up and hold that paper into place. So that's good. And so now I have something to draw on, and so it's not going to be a real fancy drawing. I'm even going to use a pen here, and hopefully I won't mess up, and because it's not a pencil here. But one of the first things I want to do is just to draw where are the plates on here. And so we have these templates, if you will, that kind of help. They're kind of clear, so I don't know how well they come out on video, but you can kind of see that this, here we go. This template right here has the outline of these metal plates here. So if I were to lay this template on here and maybe just kind of look on the underside to make sure it matches, the first part of my drawing is just to outline where the metal plates are before I try to draw the equipotentials and the electric field. So I'll hold it up for what you can see so far. So far, oh, I should ask, can you see that? You can probably see it at an angle. I don't need to lift it up. Okay, good. And so there's my plates. Now, also for my own memory here, I'm going to put pluses on them. Tell myself that that is the plus side, and this then is the minus side. And I'll even put the value on here, and I'm debating here if I should try to write upside down. Maybe not, because I'm going to scan this and give it to you, so I don't want it to look too sloppy. So I'm going to write that the potential right here on this plate is 10 volts. And the one on this plate is 0 volts. So you might say those are my first two equipotentials. the 0 volts and the 10 volts. And if I hold it up, you'll see it kind of upside down, but I'll scan it to you, and this is going to be part of what you're going to draw on top of. And so, like I said, if I tried to draw upside down, I don't think the 10 would come out real clear. All right, so now finally we're ready to kind of begin the lab. All right, so where is, say, the equipotential of 5 volts? So why don't I find that one first? And so if it'll be okay, I'm going to turn this to me and just make a little mark everywhere my underneath probe gets five volts. And maybe I'll pull it back so you can kind of see all of those points were at 5 volts. Okay. Now let me go kind of the other direction here. And at the risk of messing up my drawing for you, but trying to save a little bit of time. I know you will get bored watching me for a half hour trying to figure this all out. I'll just do that view, okay? And so the first part of this is I'm just going to connect these together and label it as 5 volts. So there is my first equipotential, well, maybe my 3 equipotentials, a 0, a 5, and a 10. Let's see if we can find the 3 volts equipotential. And so let me just, make sure my probe is touching up underneath it. And so there's a 3 volts. 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 And there's a 3 volts. Okay, and I'll go the other way. There's a 3 volts. There's a 3 volts. There's a 3 volts. So this was the part at the beginning of the intro I said wasn't sure how this was going to work out because this takes quite a bit of time. And so, but I should just do the whole thing like you guys are here. And so let me just go ahead and connect those and label it as 3 volts. I was going to do 1 volt, but in the interest of time, maybe you'll see it. And so I'm going to jump to the other side and go 7 volts. Okay. And then I'll come back and do the 1 volt. Because it's probably good to get a little more accuracy. With the 7 and the 9 volts. But let me just find a bunch of locations that all have the same voltage. Ooh, I bumped the paper. Nice. Okay, I'll pull that one back so you can kind of see. But there is then the equipotential at 7 volts. And the harder one to squeeze in here because it kind of bumps up against the plate is the 9. Ah, but it looks like I can just get the 9. That's good. Oh, looks like the 9 curves pretty tightly here. That's good. No, don't bump. Oh, yeah. Okay, let's go the other direction. Actually, one thing kind of neat about these online labs is it makes me come back and actually measure them. I haven't actually sat down and measured these in a decade. I have done it so much in the